Hello, in this video I'm going to solve the following problem for you, probability theory, on the topic of multivariate normal distribution. Suppose that x and y have two-dimensional normal distribution with means 0 and variances 1 and correlation function ρ, in which absolute value of ρ is less than 1. Let capital R and capital theta be the polar coordinates. Determine the distribution of theta. This is problem 2 on page 140 in the following book, an intermediate course in probability, 2nd edition, Springer 2009 by Alan Guth. Pause the video at this point and give it a try. Okay, so in this problem, what is wanted is the probability distribution for the variable capital theta. So this is actually what we want to calculate, the probability density function of capital theta. The standard way to do this is to calculate the joint probability distribution for capital R and capital theta, the polar coordinates, as a function of R and theta. Because if I know this, I can integrate over the R variable and go back to my question mark. But because the problem is telling us something about x and y random variables, not R and theta directly, so it motivates me first ask myself, what is the joint probability distribution for x and y? Okay? Because if I know this, I can use the transformation theorem and go backward and find this. And when I have this one, I can integrate over the R variable and go backward and get this, and I will finally have my problem solved. Okay, so this is why I want to concentrate on finding this first. And that is a very standard problem here, yes? Because what is told to us is that we know this random vector x and y is a is a random bivariate normal distribution, and I know how to find its probability density function according to the formula that is very common and it is very standard given in all probability texts. So I will write it for two-dimensional case here. So if I want to calculate the joint probability distribution of x and y, this becomes equal to 1 over 2 pi, 1 over square root of determinant of lambda here, matrix lambda here is the covariance matrix of this random vector, multiplied by the exponential of -1/2, and then I have my vector, so let me write it like this, x minus mu of x, the mean related to the random variable x, multiply, and sorry, this is the 1 by 2 matrix, and the other one is y minus mu y, multiplied by a inverse, as lambda inverse, and then multiplied by x minus mu x, and then y minus mu y. Yes. Okay, but in this problem, mu x and mu y, the means, are both equal to 0. And we know that the variances are both equal to 1 and the covariance is a ρ. So we know that the matrix lambda is a 2 by 2 matrix here. The entry here will be the variance of the random variable x. Here it's the variance of random variable y, so I can fill them up with 1 and 1 according to the problem. And we know that this one and that one are the covariance between x and y. According to the problem, I can write ρ here and ρ there. But if you see here, I need a inverse, and it's very simple to calculate the inverse of a 2 by 2 matrix. So lambda inverse is equal to 1 over determinant of this matrix, which is 1 times 1 minus ρ times ρ, which is 1 minus ρ squared, and then the adjoint of that matrix, but the adjoint of 2 by 2 matrix is very simple, The only thing I have to do is to interchange these two, but there is no change here because both of them are equal. And then I have to multiply these by a minus sign. Okay, everything is now ready. I put every information that I have in this general formula here. Okay, so this becomes equal to, so I can write f of x and y calculated at little x and little y is equal to 1 over 2 pi 1 over the determinant of lambda. The determinant of lambda is 1 minus rho squared, so I have to take the square root of 1 minus rho squared, and then multiplied by exponential minus a half, but mu x and mu y are both equal to 0, so that is just simply this matrix, and then multiplied by the lambda inverse, which is 1 minus rho squared, 1 minus rho, and 1, and then you multiply it by x and y as a column vector here. Okay, and if I want to simplify this a little bit, so this becomes 1 over 2 pi square root of 1 minus rho squared. Okay, so you see this is just a number, so if you don't mind, let me multiply it here. So this becomes exponential of minus 1 over 2 times 1 minus rho squared. And then I have 3 matrices to multiply. It's a very simple task to do. You first multiply these 2 matrices, it becomes a 2 by 1 matrix, and then you multiply it by this 1 by 2 matrix, it becomes a number at the end. If you do these simple calculations, so if you don't mind, let me do it here for you. So it becomes x and y, but if I multiply the first row by the first column, so it becomes x minus a row y, and the second column by the second row by this column, it becomes minus rho x plus y. And if I do the multiplication once more, so it becomes 1 over 2 pi square root of 1 minus rho squared, and then I have exponential. So let me write it like this. I put the minus sign here, and I put there's also here 2 1 minus rho squared, and then if I multiply this x times that, it becomes x squared minus rho xy, and then multiply this here, it becomes minus rho xy plus y squared, so this becomes minus 2 rho xy. So this becomes x squared minus 2 rho xy plus y squared. Okay, so that is my probability, the joint probability distribution for x and y. Okay, but now what I want to do, I want to use the transformation theorem to go here and find the joint probability distribution for r and theta. Of course, we know what to do here. So x, capital X, is r cosine theta, because these are just the standard polar coordinates, and y is also r sine theta. Okay, so I need to calculate the Jacobian of this transformation from the old variables x and y to the new variables. So it's simply the determinant. I have to calculate the derivative of this with respect to r, and the derivative of this with respect to theta, and write them here and there, and do the same thing for y and write them here and there, and calculate this determinant. So it is very easy. The derivative of this one with respect to r is just cosine theta. So if you don't mind, let me write it with lowercase letters here. And the other one will be minus r sine theta. The next one, the derivative of y with respect to r is just simply sine theta, and the derivative of y with respect to theta is r cosine theta. But you can see that if you calculate this determinant, it becomes this multiplied by that, so it becomes r cosine theta squared minus r sine theta times sine theta, which becomes r sine squared theta, so it becomes r, just r. Yes, so that's the Jacobian of the transformation. So what I can now write is that, and by the way, so you need to also know the support of r and theta, and you know that for the standard transformation, polar transformation, r is between 0, r should be positive, there is no upper bound for r, and then for having it 1 to 1, theta should be somewhere between 0 and 2 pi. Yes, we exclude 2 pi so that we do not affect the injectivity, the one-to-oneness of this transformation, so that we can use the transformation theorem without any problems. Okay, so what I can write is that f r capital theta r theta is equal to f of x and y. In principle, I have to write x and y here, but of course I have to express them in terms of the new variables r and theta, and these are standard ones, so it becomes r cosine theta. So let me open up a little bit of space here. R cosine theta and r sine theta, but I have to multiply by the absolute value of the Jacobian of the transformation. But because r is positive in the polar form, I don't need absolute value, I just write r. Okay, but this is very simple now, because I know what is the joint probability distribution for capital X and capital Y for x and y. This is my formula, but instead of x I have this, and instead of y I have this. It doesn't matter, I take them with me and put them here. Okay, so this becomes what? It becomes, I have a factor here, and I have also r here. So if you don't mind, let me write it as r over 2 pi square root of 1 minus rho squared. And then I have exponential minus, the denominator is not sensitive to x and y, so let me just copy and paste that. But here, let us do some parts in our head. So x squared plus y squared, if x is this and y is this, of course, is r squared. And this one becomes 2 rho sine theta cosine theta times r squared. But 2 sine theta cosine theta can also be written as sine 2 theta. And there is an r squared there. So what happens, it becomes r squared minus rho r squared sine 2 theta. Yes, so this is what we have here. So I was able to find this, and what is left for me is just to go one step back and integrate with respect to r to be able to find the probability distribution for theta. Okay, so if you don't mind, let me take this with me to the other page and continue there. Yes. Okay. Okay, so now what we are supposed to do, we have to integrate this function in this function with respect to variable r. And what we gain is exactly what we want. Okay, so here I have to write this formula first for you. F of capital theta for any theta between 0 and 2 pi, 0 included, 2 pi excluded. This becomes integral in principle from minus infinity to infinity, and then I have f of r and theta, r theta, but with respect to the other variables. So here I want to find the marginal distribution function with respect to theta. I have to integrate over the other variable, in this case r. Yes. So if I want to continue forward, you know that r is positive, so it means that if r is negative, this is 0. So it means that this will be limited to only from 0 to infinity f r theta r and theta and dr. So, and this function is this function that you see here. Okay, so this one is a constant. I can pull it out from my integral. So this becomes 1 over 2 pi square root of 1 minus rho squared. And then I have integral from 0 to infinity. And then I have 1r. And I have this exponential. But in this exponential, to make things a little bit simpler, I factor r squared here. And if you don't mind, let me write it with normal exponential function form. So it becomes to the power of minus 1 minus rho sine 2 theta divided by 2 1 minus rho squared, and then what I have here is r squared, and then finally I have dr. It is mentioned in the problem that absolute value of rho is less than 1, so that's a good news, because what I get is that this expression is positive if I respect that condition. Okay? So if that is positive, for simplicity of writing only, so if you don't mind, let me give it a name, because I want to emphasize this is positive, so if you don't mind, let me write it as c squared. Okay, this can be replaced by c squared. It makes life a little bit simpler for us to write it simpler. So this becomes 1 over 2 pi square root of 1 minus rho squared, and then I have integral from 0 to infinity, and I have r times e to the power of minus c squared r squared, and I have dr. Okay, but this is a very simple integral to calculate, so here I can take c squared r squared to be my new variable, so let me call it t, for example, differentiate both sides, so it becomes 2 c squared r dr is equal to dt. So this means that r dr is 1/2 of 1 over 2 c squared dt. Okay, so this means that instead of r dr, I can put this expression, but that one is also a constant. I can pull it out, so this becomes 1 over 2 pi square root of 1 minus rho squared multiplied by 1 over 2 c squared integral. But that's also important to know that if the lower limit for r is 0, if I put r 0, the lower limit for t becomes also 0. And if the upper limit for r is infinity, if I put it infinity here, it becomes positive infinity because this one is positive. But that was important to really know that this expression is positive. So that is why they have told us that the absolute value of rho is smaller than 1. Okay, so then this becomes plus infinity, 0, and then I have e to the power of minus t dt. Okay, but that's very simple. So this becomes 1 over, I multiply 2 by 2, so it becomes 4 pi square root of 1 minus rho squared, and then I have c squared, and then this becomes minus e to power minus t, because that is the primitive function for this function is simply this, and then I have to go from 0 to infinity, but that simply becomes 1. Yes, this is just simply 1, because if I put infinity it becomes 0, if I put 0 it becomes 1. So that is the final answer to the problem actually, but I have to put this c2 back, so it becomes 1 over 4 pi square root of 1 minus rho squared multiplied by the reciprocal of c squared. So I have to replace the numerator and denominator here. So it becomes 2 1 minus rho squared divided by 1 minus rho sine 2 theta. Yes? So here this 2 and that 4 cancel. This one can be written as 1 minus rho squared times 1 minus rho squared. This one will cancel that one. Yes? So we have it in simplified version finally. So the marginal distribution function for theta is indeed equal to square root of 1 minus rho squared divided by 2 pi multiplied by 1 minus rho sine 2 theta. Yes, so that is what we have. Okay, so we have this as the probable distribution function. Okay, of course we have to also mention that theta is between 0 and 2 pi, yes, because we solved everything based on this assumption that r and theta are just the standard polar coordinates, and we know that theta lies between 0 and 2 pi. So at the end, this should also be included in the answer. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.